Welcome to this explainer. Okay, so naval architects have a massive problem. Before a single piece of steel is ever cut, a gigantic, complex ship essentially has to exist entirely in their minds. It's basically the ultimate chicken and egg paradox of engineering, because every single physical and performance characteristic has to be perfectly dialed in before construction can even begin. I want you to picture this. You're an engineer staring at a completely blank screen, trying to figure out how to design a 300-meter steel vessel. Where do you even begin? It seems like a totally impossible problem because a ship operates in such a highly dynamic environment that every design parameter affects every other parameter. There is literally no obvious place to start.
Let's just look at this list for a second, because it perfectly captures the sheer chaos of it all. You need the hull dimensions to calculate stability, right? But you need stability to actually size the hull. You need engine power to set the fuel tank size, but changing the tank size changes the entire ship's displacement, which, you guessed it, changes the power you need from the engine. Everything depends on everything else. You simply cannot optimize one single thing in isolation without triggering this massive chain reaction across the entire vessel.
Section 1. Enter the design spiral, bringing order to the chaos of shipbuilding.
So what's the solution to all this? It's something called the design spiral. This is a brilliant iterative framework that systematically works through these interconnected design parameters in a strict sequence. Instead of trying to solve the entire puzzle all at once, the spiral brings order to the chaos. It essentially forces designers to balance all the constraints simultaneously by looping through them until the solution converges. Honestly, it's no wonder our source material calls this process one of the most elegant frameworks in all of engineering. It really is. This spiral is exactly what saves shipbuilders from making catastrophic errors. Think about it. A change on a blueprint costs almost nothing, but a change during actual physical construction, that can delay delivery by months and cost an absolute fortune.
Section 2. Walking the first loop. Taking a ship from a first guess to a blueprint.
So here is how it actually plays out in practice. You start with a first, really rough guess at the ship's dimensions. Then, you use those dimensions to sketch out the general arrangement. That arrangement gives you an estimate for the structural mass. The mass tells you the displacement, which then dictates the engine power you'll need to hit your target speed. Next up is stability. Does the ship actually stay upright? And finally, you run the cost. As you can see, everything is seamlessly connected. But wait, here is the catch. Once you hit that final cost metric, you don't just pack up and go home. No way. You take everything you just learned from that very first pass, you revise your initial dimension guess, the loop tightens, and you go right back to the start to run the entire sequence all over again. Section 3. Reaching design convergence. When the numbers finally stop changing. With each trip around that spiral, you're getting a more and more accurate answer. The changes between each loop get smaller and smaller. Let's say you start with a 185-meter guess for your length. The next loop drops it to 183 meters. Then maybe it ticks back up just a bit to 183.2, until finally it stabilizes right here at exactly 183.5 meters. And that right there is the magic moment. When the numbers stop changing significantly from one loop to the next, your design has officially converged. You haven't just found a design that works, you've actually found the most economically efficient solution that satisfies every single constraint simultaneously. The blueprint is locked in. Section 4. The ultimate objective. Building the most profitable ship, not just the biggest. Now you might be wondering, why go through all this exhausting, endless iteration? Why not just over-engineer a massively safe steel box and call it a day? Well, because any ship that's big enough can carry cargo. But an owner absolutely does not want an over-engineered vessel loaded with wasted steel, way too much engine power, and incredibly bloated costs. They want the leanest, most profitable ship possible. Literally the absolute minimum ship that safely gets the job done. The spiral is what balances that safety, performance, and cost all at the exact same time.
To wrap up this explainer, I want to leave you with a bit of a provocative thought to ponder. If the design spiral is this essential, complex framework, what kind of digital tool makes balancing these millions of shifting data points even possible today? Because manually calculating this massive web of variables by hand would literally take years. The answer lies in modern CAD and CAM software, but that is a totally fascinating story for our next explainer. Thanks for joining me on this deep dive into the blueprint of the sea.